Welcome everyone. Today we are going to have our lecture series on solution of civil services mathematics optional 2019. We have already covered ordinary differential equation, vector analysis and partial differential equation. Today we are going to take another important and very simple topic called complex analysis. In 2019, complex analysis was asked for 45 marks, in 2018 it was asked for 40 marks, and in 2017 it was asked for 55 marks. Now we are going to take the first question, that says question number 1D. It was asked in compulsory. It is asking, suppose fz is analytic function on a domain D in C and satisfied the equation imaginary part of fz is equal to real part of fz whole square, where z belongs to D, so that fz is constant in D. 10 marks. Now such kind of question are very important question to solve, and now I'm going to solve it. There are two methods to solve this question. I can work in polar coordinates and polar form, and I can also work in Cartesian coordinate. So I'm going to write my solution over here. So we have given f of z. So here we are taking the polar form. So we are going to use Cauchy-Riemann equation. That is r ur is equal to v theta and r vr is equal to minus of u theta, where ur is dou u by dou r and u theta is equal to dou u by dou theta. Similarly, vr is equal to dou v by dou r and v theta is equal to dou v by dou theta. Okay, so from here we'll first formulate what is given to us. So f of z is equal to u plus iv. Alright, and we have given imaginary part of function fz. What is the imaginary part? V is equal to real part fz. Real part is u, that's square. So we are given this. So this is the equation number 1. V is equal to u square. So I can differentiate equation 1 with respect to r. So I can write this Vr is equal to 2 times u ur. I will call this my equation number 2. Now again I will differentiate equation 1 with respect to what? With respect to theta. So we get this as v theta is equal to 2u u theta. I will call this my equation 3. Alright. Now I'm going to divide equation 2 and equation 3. So if I do that, divide equation 2 by 3. So we get, what is equation 2? Vr is equal to 2u ur. So we will write Vr is equal to 2u ur and v theta is equal to 2u u theta. So this and this get cancelled. Okay, so we can see here Vr is equal to how much? From here you can see Vr is equal to minus u theta by r. So I can write this minus u theta by r. Okay, and what is v theta? V theta is r u r. So I will write this as r u r is equal to ur u theta. So we can see over here, we can write this as u theta square minus of r square is equal to ur. So we are getting this as how much? We are getting this as r square ur whole square plus u theta square is equal to 0. Okay, now we know u theta from here is VR. So that is minus. If I take the square of this, it becomes R square VR square. So this becomes R square UR square, and this becomes again R square VR square. So we get UR square plus VR square is equal to 0. Alright, so if we take the derivative of this function over here, so we can write this in polar form. This is e to the power minus I theta into UR plus I VR. Now if I take modulus of this, so this becomes modulus of e to the power minus I theta and under root of UR square plus VR square. Alright, now we have already found our UR square plus VR square. So this is equal to 0. And modulus of e to the power minus theta is how much? 1. So we get f dash z modulus is equal to 0. That means if we integrate this, this becomes fz is equal to, say, a constant. So we have proved our claim, and I have used polar form. You can use Cartesian form also. When you are going to use Cartesian form, you can use this equation: ux is equal to vy and uy is equal to minus of vx. Same thing will follow. We will write f dash of z is equal to ux plus ivx, and again we are going to use this same thing, and here we will. So this is the second question. It is question number 2D. Here we have to show that an isolated singular point z0 of a point of a function fz is a pole of order m if and only if fz can be written in the form fz is equal to phi z by z minus z0 to the power m, where phi z is analytic and non-zero at z0. Also, we have to find the residue at z is equal to z0 of this fz function, that is equal to phi m power m minus 1 z0 by m minus 1 factorial if m is greater than equal to 1, and this will ask for 15 marks. So this is a sort of theorem we have to prove, and we have given that f of z is having a pole of order m, and there exists a dilated neighborhood of z0 in the region mod z minus z0 that lies from 0 to r, and our r is greater than 0. Then there exists, then fz has a Laurent series expansion that is written as f of z is equal to summation of n is equal to 0 to infinity a n z minus z0 to the power n plus p1 by z minus z0 to the power 1 plus b2 by z minus z0 to the power 2, and this will go on till bm z minus z0 to the power m, and here bm is not equal to 0. So if I take this z minus z0 to the power m outside and common, this can be written as z minus z0 to the power m, and this summation can be written as n is equal to 0 to infinity a n z minus z0. Since we have divided, so we will multiply it all there. So this z minus z0 to the power m is get added, and the indices will be added. So m plus n plus, we can write this as b1 by z minus z naught. We have taken this. So we can write this as z minus z naught m minus 1 plus b2 z minus z naught m minus 2 till bm. So this we have been able to express in terms of a phi z function. So we can write this as z minus z naught to the power m into phi of z, the whole term that we have written. So we can write this as f z is equal to 1 by z minus z naught to the power m by phi z. So we have proved our claim for the first part. Now we are going to do it for the second part. So I can write this as phi of z is equal to z minus z naught to the power m f of z. And here phi of z is analytic and is non-zero at z naught. So that means phi of z is analytic and phi of z naught is not equal to 0. Phi of z naught is not equal to 0. So now from here on we are going to proceed for the second part. So I am going to erase some of the portions over here. So I am going to copy it over here. Phi of z is equal to z minus z naught to the power m by f of z. So I am going to now use the Taylor series to expand phi of z at z naught. So this can be written as phi of z naught plus z minus z naught phi dash z naught divided by 1 factorial plus z minus z naught whole by 2 factorial phi double dash z naught. And similarly you can write this as by factorial phi of z naught. So you can write of z is equal to phi of z divided by z minus z naught to the power m. So this becomes phi of z naught divided by z minus z naught to the power m plus phi dash of z naught divided by 1 factorial into z minus z naught m to the power 1, because here m we are dividing, so I am taking this numerator into denominator, so this there will be minus 1, and this can be written as phi double dash z naught by 2 factorial z minus z naught, and this can be written as square m minus 2, and similarly we can go till phi m. If we go for m minus 1, here I have written m till m, so if I go for m minus 1, so this becomes this, and this becomes m minus 1 factorial, and this becomes z minus z naught m minus of m. So this we are getting. So I will just introduce one more term for the sake of simplicity, that is I can write this as my term over here, and then we are going to get our values. So now we have to we have known that it is analytic and non-zero over here. So we have to find the residue at z is equal to z naught. So that is equal to coefficient of 1 by z minus z naught. So what is the coefficient of 1 by z minus z naught? We can write it from here. This is pi m minus 1 z naught divided by m minus 1 factorial. So this is what we are supposed to prove, that the residue, and to prove it for here we can check it for m is equal to 1. So it is going to be, for m is equal to 1, 5 of 0 divided by 1. So effectively we have to just put the value of that particular at that point if it is z naught. So we have proved our claim. This is the theorem, and we can do it like this. Now I am going to take the next question. So this is question number 3c. We have to evaluate the integral real part of z square tz from 0 to 2 plus 4i along the curve C, where C is a parabola, y is equal to x square. So this is a simple line integral, and what we have to do over here is, first of all, we must understand the curve. The curve is a parabola, y is equal to x square, and it is from 0, 0 on. If I draw on an Argand plane, this is my 2, and if I call this my 4, this is the point 2, 4. So we have to find the integral from 0, 0 to 2, 4. Now I will try to parameterize this form. So I will write my x and y as, say, if I am putting x is equal to t, that means y is equal to x square. So t square is the point for this. Now I will integrate it. Okay. Before that, I will find z and tz. So z is x plus iy. So z square is how much? X square minus y square plus 2i xy. And here I have to take the only real part of this. The real part is only x square minus y square. Now, if I am going to put z is equal to x plus iy, and I can put the value of x. X value is t plus I. What is the value of y? Is t square. Okay. So I can take the derivative of this. Tz is equal to dt plus 2it dt. Now I have actually, what I have done, I have just changed everything to a parameter t. So this will be a simple line integral. And what is this value? Z is real part of z square is equal to x square minus y square. So I will put the value of x as t. So x square is t square. And what is the value of y? T square. So y square is going to be t to the power 4 dt. We are going to write. Now I have written till this part. What is dz? Dz is dt plus 2it dt. So what I will do, I will take common dt 1 plus 2it dt. Now I am only remaining with my parameter t. So I will put, when x is equal to 0, t is equal to 0. When x is equal to 2, t is equal to how much? 2. You can see from here. Okay. So we have got our values. T is equal to 0 to how much? 2. So I will now integrate this one. So this is t square minus t to the power 4 plus, I am going to write the imaginary part over here. So this is 2t cube minus 2t to the power 4 dt. So this is t to the power 3 by 3 minus t to the power 5 by 5 plus I times 2 to the power 4 by 4 minus of 2 to the power 5 by, so this is here 5, so we have to write over here 5. So this is 6 by 6, and we are going to put the limits. So if we put the limit on this part, so we will get this as minus of 56 divided by 50 minus of 40 by 3i. So this is the answer to this question. Now I'm going to take the next question. Okay. So this is the last question. That is question number 4b. We have to obtain the first three terms of a Laurent series expansion of function fz is equal to 1 by e to the power z minus 1 about point z is equal to 0 valid in the region mod z lies from 0 to 2 pi. This is the constraint. Ask for 10 marks. So what will I do? I will write my solution f of z and I will expand e to the power z. This is 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial till, and I'll lose this. So this one and this one will get cancelled. So I can write this as f of z is equal to, I can take z as common. This become 1 plus z by 2 factorial plus z square by 3 factorial plus z cube by 4 factorial and so on. Suppose if I take the whole term, this one, as say some function of phi of z, 1 plus z by 2 factorial plus z square by 3 factorial plus z cube by 4 factorial. Now we can see over here that this phi of z is analytic, because we have to be very sure whether it is in this domain or not. Is analytic in, because you put any value that will lie within the limits of 2 into pi. So if you put 0, then also it is lying. If you put any value, that will lie within this. So this is the constraint. Many of the solutions which is found on internet, they are writing it as mod z. This is blatantly wrong, not even given in the question. So the clarity is not and that on such solutions. So it's very much defined over here and we can readily see from here. So now I am going to proceed further, and we can see over here that about z is equal to 0, these value will be small, so we can write this geometric series, geometric progression, we are going to use it. Now if I am going to take x is equal to z by 2 factorial plus z by 2 factorial plus z square by 3 factorial and so on. So I can expand it as 1 plus x, because it is so small that I can write it as 1 minus x plus x square and so on. So I have taken this from here. So this becomes f of z is equal to 1 by z into 1 plus x. I am going to use this and I will do it on the upper portion once more. So to write it over here. So f of z can be written as 1 by z into 1 minus x plus x square and so on. We have to only be concerned with 3 terms, so we are not going further. So if I write this as 1 by z and expand 1, what is x? Z by 2 factorial plus z square by 3 factorial, so on. Okay. So now I have to find the x square. So this is z by 2 factorial plus z by 2 z square by 3 factorial and so on square plus z by 2 factorial plus z by 2 z square by 3 factorial and so on. I will take the cube of this. Only concerned with 3 terms, so I will just try to find on those terms only. First we are already getting over here. Now for z terms, it is how much? Minus z by 2. Okay. Now I am going to collect the coefficient of z square. You can see over here 1 by. Now I am going to square this one, z square. Z square by how much? 2 factorial square. So 2 factorial is 2. So 2 square is 4. So this becomes 1 by 4. and here we are having few other terms, so z square just coefficient and still here. Similarly for z cube we have to factor this. There are others, we are only concerned with 3 terms, that is what they are asking, so I am not going to write the other terms of z square. So this is 1 by z into 1 minus z by 2, and I am going to find this value. 1 by 4 minus 1 by how much? 1 by 4 minus 1 by 6, so this is effectively 12, so 3 minus of 2, 1 by 12, so this gives me z square by 12, and the terms of z cube, they are negligibly small, so I will denote it by capital O, that is negligibly small, only concerned with 3 terms, so this becomes 1 by z minus 1 by 2 plus z by 12. So this is the first 3 terms of the Laurent series. So questions that we are asking complex analysis, we are again very simple this year, but we have to be very mindful of small mistakes that we should not taking place. Like if it is given mod z lies from 0 to 2 pi, you cannot take it 1 by your own choice and try to do it and seeing the blatantly wrong solutions on the internet. So now with this we end the complex analysis. If you really want to have more solutions on different topic, please subscribe our channel and write in the comment section whatever doubts you have with regard to this and what in times to come we are going to provide. Please be interactive with us. We are here to help you out in this course, and thank you for watching. Please like, share and subscribe.